One, 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 one. One, 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 one. Okay, welcome everyone. We'll be starting the next session. Welcome to the stage Ed. He will tell us about Pygambit and GT Draw, and a little bit about game theory. So please have a huge round of applause for him.
Hello, yes, thank you. So I'm Ed. I'm a research software engineer, or I was. I've actually just left the job that was working on this project, but I'm going to be talking a little bit about these two packages for game theory called PyGambit and GTDraw. You may notice that the name of the second one has changed since the program. That's because we finally released it on PyPy and we wanted to come up with a name that had game theory somewhere in it. Anyway, it's going to be called GTDraw. It is called GTDraw. So these are both packages that are part of the sort of Gambit suite of software tools, which is what I'm going to talk about today. So before I talk about Gambit and PyGambit in particular, I'll just do a little bit of introduction to game theory. So I'm a software engineer. I'm not a mathematician with a game theory background. So the level of detail I'm going to go into today is just to help you understand how the packages work. But one of the sort of main use cases of PyGambit and Gambit in general now is for learning anyway. So as you'll see, the sort of once I get to the notebook demo, it's adapted from some of the tutorials and documentation you can find online for the package anyway. And so this is, yeah, you should find this interesting regardless of your knowledge of game theory. But what is game theory? So game theory comes from economics. It goes back to the 1950s with John Nash. And basically, it's concerning any kind of scenario that you can model mathematically where there are strategic interactions between players. So players in the original sense would have been people in the economy. So that's where it comes from, economics. But it's also been used in biology and ecology to model animal behavior. And then it's increasingly of relevance again now in the AI era. So there's a lot of work going on in cybersecurity, multi-agent systems. And again, these are scenarios taking place where you can think of AI agents interacting in a strategic way. So we can use game theory for those fields as well. So Gambit, as I mentioned, is a suite of software tools. It's in particular focused on what we call finite non-cooperative games. So what do we mean by that? Finite means a game that has an end or many ends where each of the players gets some kind of payoff. And non-cooperative is exactly what you think it means. It means the players are adversarial. They are competing with one another. So Gambit is a suite of tools, as I said, is used by researchers, but it's also used by teachers and sort of university academics for learning about game theory. But as I'll go on to show, it's also used as a useful tool in computer science for calculating Nash equilibria, which I will explain in a moment. Before I do, just to take you back in time a little bit, I don't personally remember the 1980s. Some of you here may do, but this goes all the way back to the 1980s. And in its most recent iteration, it's been developed at the Alan Turing Institute, where I was working until recently. And it's really been, the most recent project has really been around updating the PyGambit Python API, making sure it's as user-friendly as possible, that people using it for calculating Nash equilibria and people using it as a learning tool alike can come to it and understand what's going on. I'll also highlight a little bit at the bottom there some other work that's going on. So some of my colleagues have been working on sort of LLM prompting framework for extensive games in game theory. So this is using LLMs to generate the PyGambit code, which is the code that for the package that I'm about to demonstrate. So that's not another ongoing area of research, getting like an accurate game description to code translation layer. That's not what I'll be talking about today. What I'll be talking about today is, as I said, the PyGambit package. Its general sort of uses, how to use it, and yeah, another thing we've been working on is building the open source community. So if people are interested, we'll probably we'll be wanting people to contribute if they're interested. So what I'll show today is PyGambit and its two core features, which are number one, constructing a game in the game theory sense in just a few lines of code, and then secondly, using that game and computing the Nash equilibria. with which can be done with various algorithms. So the Nash equilibria is essentially a scenario where all of the players in the game are using a strategy for which they have no incentive to deviate that strategy. So it's become an equilibria. It's kind of like a stable state of the gameplay. Let me close that. Oh, you can't see it. Okay, and then finally, I'll talk a little bit about how PyGambit is interoperable with other packages in Python scientific computing ecosystem. And I'll look a little bit at a particular package from DeepMind called OpenSpiel, which is also used in game theory. Okay, so I'm going to give a little bit of a live demo, but it is just running through notebook cells, so hopefully nothing can go wrong. So I'm going to can everyone see that? Okay, is that big enough? Yes. Okay. So I'm going to walk through the construction of a game in the game theory sense, so you can get an understanding of that. And then I'll literally walk through the construction with PyGambit code. So first, let me describe the game that I want to create. So we have this example game. It's called Stripped Down Poker. That's not to be confused with Strip Poker, which is something entirely different. Okay, you want it to be bigger? Okay, let me see. Better? Yeah, okay. Okay, so Stripped Down Poker is very simple. So it's a two-player game. We're going to call our players Alice and Bob. They've got a deck of cards, and there are two cards in the deck, King and Queen. And either a king or queen is going to be dealt with 50% probability. So the game starts with both players putting $1 in the pot. A card is dealt at random to Alice with 50% probability king or 50% probability queen. Obviously, king is better than queen in cards. So Alice gets to see what card she has, and Bob, player 2, crucially does not observe the card. Second step is Alice, player 1, gets a turn. So she has to take an action of either bet or fold. If she chooses to fold, obviously she loses, Bob wins. If she chooses to bet, then she's adding another $1 to the pot. If Alice does bet, then it's Bob's turn to act. So he's got two actions as well, call or fold. Again, obviously, if he folds, then Alice wins. If he calls, then he adds his $1 to the pot. And then finally, if we've got to that point where they've both bet and then called, we see whether the card is a king or a queen. And if it's king, then Alice wins. And if it's queen, then Bob wins. Okay, so this is a very simple sort of what we call an extensive form game. And that will become apparent what that means in a second. So, okay, I'm going to have to run notebook cells and talk into the mic at the same time. How do we create this kind of game with PyGambit in just a few lines of code? So the first thing we need to do is create a new game object, which we do with this new tree function. Very simply, we create the two players, give it a title. And the first thing we notice here is if we look at the players that are now in the game, we've got actually three players. So we've got Alice and Bob, the players we made, but we've also got this chance player. And this is a crucial thing in game theory. So the chance player is basically models nature, so something that's happening outside the player's control. And so in that respect, the first move in the game is actually for a card to be dealt. So if you remember, we've got the two cards, king and queen, and we're using this append move function to the root node, and specifically for the chance player, so not one of the actual players. And the actions are king or queen, and we're giving those actions probabilities of 1/2 and 1/2. So this draw function here is the GT draw package, which we're using to visualize the PyGambit game. You'll see a bit more of that in a moment. Okay, so we have the first part of our game, which is just the card being dealt. Now we want to model Alice's moves. So in this case, what we're going to do is use a loop. So we're going for node in the children of root, and we're actually appending the move to both of them. So we do that now. So what we'll see here is that we've got Alice's actions of bet and fold, and they're appended to both of the possible nodes where she could be making her decision. So in game theory, these are called information sets. And basically, Alice has two information sets, one where the king was dealt and one where the queen was dealt. But in both cases, she has the same two possible actions she can take. Now, this is important because when we get to Bob, we want to append his moves. Bob, if you remember, doesn't know what card has been dealt. So he's only got a single information set in game theory speak. So the way we do that in PyGambit is we append move again, but instead of looping through, as we did earlier, all of the nodes, we're now just going to do append move for the list of nodes. So these are the two nodes here that we're applying it to. And what you get now is that for Bob's two action nodes, they're sort of linked by this oval here. And that's because they're part of the same information set. So basically that just means that Bob doesn't know whether he's at this node or this node. Okay. So the next thing we have to do is add some outcomes for our game. So again, very simple, we have an add outcome function, and we're going to add the different possible payoff, the payoffs for Bob and Alice that we have in each possible end to the game, each terminal state. And sorry, the Wi-Fi keeps coming up. Okay, so yeah, let's do that. So we've created these four possible outcomes. The first one we've called win big. So this is according to Alice player one, where she gets the $2. There's a possibility of her getting the smaller win, and there's a possibility of her losing big or losing small. And then finally, we just need to apply each of these to all of the terminal nodes of the game. So there are 6 possible ends to the game, which you can see in the visual. And we're just applying each of those outcomes that we defined to each of those terminal nodes of the game. And if we draw the final version of our game, it looks a bit like this. So that's stripped down poker, and that's sort of an introduction to how you can create a simple, what we call extensive form game in game theory with PyGambit, and also visualize it with GTDraw, which is this draw function here. Yeah, just behind the scenes then, so maybe I'll talk about this now. So this particular, the GTDraw package, which as you can see is just taking the PyGambit game object, and then you can apply different visual settings. At the moment, all we've done is set the color scheme, but there are lots of other options. So if I look at there's a nice little GUI we've added to GTDraw. There's lots of other options you can change, like you can change the layout to horizontal, you can change the scale, increase it, decrease it, and lots of other aesthetic options. And basically the reason we created this package was so that people working in game theory who are creating publications and want to make a nice graphic of their game can do so and have control over that. Is using LaTeX under the hood, so it's just like a Python package that wraps LaTeX, and there's a format for defining the games, but you can create the game with PyGambit in a few lines of code, which is the best way to do it. Okay, so moving on to the other thing that PyGambit is used for. So as well as constructing a game, the other thing I mentioned it can do is it has a suite of algorithms for computing the Nash equilibria of games. So a Nash equilibria, to remind you, is like a stable situation where no player has any incentive to deviate their strategy. And so some games have many Nash equilibria. This one just has one. Before I run that, I'll mention that there's a number of different algorithms available in PyGambit, and we're just going to demonstrate one of them today. Again, I'm not the expert in game theory and the mathematics of it, so if you're interested, take a look at the documentation. But we're just going to run this one, which is the LCP solve, which is computes Nash equilibria by finding a solution to linear complementarity problem. So what you get when you just plug in our game, G, which is our stripped down poker game, into the LCP solve, is you get this result object. Okay, so what is this? What this shows us first and foremost is, as I mentioned, for this particular game, there's just one equilibria found. There could be more than that for other games. And if we index the equilibria object by the player name, what you get is this mixed behavior object. So, okay, what does that mean? So mixed behavior profile, as we call it, specifies for each of the information sets in the game the probability distribution over actions at that information set. Again, what does that mean exactly? Well, if we look at it, we get this 1, 0, and then 1/3, 2/3. So that's Alice, player 1, for our stripped down poker game. So what does that mean exactly? Basically, what that means is that at the first information set, Alice plays bet with probability 1, fold with probability 0. At the second information set, Alice plays bet with probability 1/3, fold with probability 2/3. So that's quite intuitive if we look back at our graphic. Basically, the first information set, which is that Alice has, which is this one here, she was dealt the king. So essentially, she's always going to bet when she's dealt the king. When she's dealt the queen, it's 1/3, 2/3. So she's going to bluff by betting 1/3 of the time and fold 2/3 of the time. So that's her strategy according to this Nash equilibria. So we can also look at Bob, player 2's strategy. Again, we've only got one information set here instead of two, as we explained earlier. So it's 2/3, 1/3. Again, that means that he's going to play call with 2/3 and fold with 1/3. So if you imagine you're Bob and you're either here or you're here, you don't know whether the king or queen has been dealt. Basically, you're going to call 1/3 of the time, chance it. Is that right? Yes, you're going to call 2/3 of the time and you're going to fold 1/3 of the time. So that apparently is the equilibrium. That are the two strategies of the two players according to this equilibria that the LCP solve found. Okay, so that tells you how. So what I've just demonstrated there is how to construct games with PyGambit, visualize them with GTdraw, and then compute the Nash equilibria with PyGambit. The other thing I wanted to demonstrate was interoperability with this other package called OpenSpiel. So as I mentioned earlier, this is PySpiel. It's a package from DeepMind that's also used for game theory. And very simply, you can just load the game that we defined earlier in Gambit in OpenSpiel. They're pretty interoperable. Although, having said that, there's quite a lot of work behind the scenes to still make that possible. So if anyone's interested in becoming a contributor, there's still some ongoing work on GitHub around that. But what does so OpenSpiel is like a reinforcement learning package. So unlike Gambit, which has this suite of like classical algorithms for determining Nash equilibria, the OpenSpiel package is a reinforcement learning package, and it can be used to like train agents versus via self-play. So what I'm going to demonstrate here with this code cell is literally just one of the features of OpenSpiel that PyGambit doesn't have, which is that you can iteratively like step through the game. So what we have here is the game sort of has like a state, and you can then choose what move what action each player takes as you go along. So all I'm doing here is just simulating some example playthroughs. So with our strip poker game, it's not strip poker, strip down poker game, if the queen is dealt and then Alice bets and then Bob folds, these are the payouts you get. So you can imagine that that's a very powerful tool that you're able to play through the games like that for reinforcement learning. So obviously, I'm not going to talk about that in details outside the scope of this talk, but just to highlight with an even simpler game, which is rock, paper, scissors, how you might converge on the same kind of Nash equilibria you can get through Pi Gambit's algorithms via some of the reinforcement learning or learning strategies available in OpenSpiel. So this game, rock, paper, scissors, it's in game theory, we call this a strategic form or normal form game, which in as a two-player game is just represented by a table instead of the tree structure we saw for the extensive form games. Pretty self-explanatory here. If rock plays rock, then both players get 0. If rock plays paper, then the player that did rock gets -1 and the player that gets paper gets 1. It's a very simple game to visualize and to represent. In Pi Gambit and in OpenSpiel, you can easily do a playthrough. In here, we're just simulating rock versus paper. Very simple. Okay, so if we plug in that game into Pi Gambit's LCP solve, the equilibria that is found is quite intuitively both players will always play each action with probability 1/3. So both players who are playing rock, paper, scissors are going to choose rock, paper, and scissors 1/3 of the time, and that's those are stable strategies, and they represent an equilibria. So I just wanted to demonstrate with replicated dynamics in OpenSpiel how over time you can converge on an equilibria even if you don't start there. So what I'm going to do is start both players with a strategy profile, choosing rock 30% of the time, paper 30% of the time, but scissors 40% of the time. So I'll just run this code and ignore that. But yeah, if you see here, I've put in 0.3, 0.3, 0.4. So what if we have both players playing scissors 40% of the time? Basically, what that means is that rock is a good strategy. So over time steps, the players start playing rock more often. Eventually, rock becomes the dominant strategy, and in that scenario, scissors becomes a good strategy, and so rock goes down. Or rather, paper becomes a good strategy, and so paper goes up, rock goes down. So it's just a very simple way of visualizing using replicator dynamics. And if we then just plot the sort of average strategy over time, you can see it begins to converge on the 1/3, which is the same we found through the traditional sort of LCP algorithm. So the reason I wanted to show this is just, imagine you have like not a simple game like the two that I've shown today, but like a very complex game you've defined that isn't computationally tractable through one of the Nash equilibrium algorithms you might find in Pi Gambit. That's when you might come to something like OpenSpiel, get the agents to do self-play, some kind of reinforcement learning, and then eventually you'll find your equilibria. So if we just plug in our equilibria of the 1/3, 1/3, 1/3 strategy, you see that there's no deviation over time. The players are never incentivized to change from that exact equilibria if that's what the starting point is. Okay, so don't play from start, play from current slide. Just a few final things then. So one of the things we've added to Pi Gambit since developing the GT Draw package is this catalog of games. So on the Pi Gambit website, there's a whole list, and this is something that's hopefully as the package becomes like bigger in the open source community, more and more people will update. But you can look at like there's games here that have been added from textbooks and papers and so on, and they have descriptions and visuals of the game. and they can be very easily loaded with one line of code in Pygambit. Okay, I think we're almost out of time, so just finish up by saying your new contributors are welcome. And yeah, thanks to the team.
Okay, thank you for the presentation. Do we have any questions?
I have one question. Thank you for your presentation. I'm not in this field, obviously, so I would like to ask for any applications that you could maybe use in some real world problems, or just this is purely just for scientific purposes.
That's a really good question. I think it is something that's I think game theory as a field is very academic. Certainly with the application to economics, although people who work in the field might dispute that, I don't know. I think just going back to the first slide, possibly this is where the action is now. So again, exactly how academic this is versus real world applied, it's a good question. You'd have to ask someone who's working in cybersecurity, thinking about multi-agent systems, I don't know. Yeah, any sort of competitive situation you can find. I think the answer is it has some practical applications, but there's a lot of academic theory behind it, and I don't personally have a good example. So.
I would think, for example, designing like card games. Right, that might be one application, because there is now a huge market for designing, card games and board games that might be helpful with balancing this sort of stuff.
Yeah, it's a good point. Like, I don't know, like people designing poker AIs, maybe they're using game theory. It's a good point. Yeah.
Okay, do we have more questions?
Yeah, for the talk, I have a question. What is the size of the problems that your package can handle?
That's a great question. I think it's something that that needs to be better explored by users. So at the moment, they're kind of, as I said, this is a package that's come out of like game theory and academia. So there are bigger games than the ones that I've shown, like ones that become large enough that it's difficult to visualize. But they are, 3 or 4 player games with, I don't know, 20 to 100 actions or something. But these are not like, I don't know. This is why I tried to present the point that there is a cutoff point somewhere where you might use those algorithms versus when you might switch to reinforcement learning. I don't know exactly where it is. So I think that's something that someone who's used it in practice rather than me, who've just been sort of the developer, would be a better place to answer. But yeah, it's a great question.
Thanks.
Okay. We have time for one more question. So.
Thank you. Thank you for the presentation. I think in terms of the real world applications, you're going to find that auction design uses a lot of game theory, negotiating salaries. You can imagine that anybody wants the highest price that you can get, and the other person perhaps wants to give you the least. So you have to assume a couple of things from the players, in a way. And Ed pointed it out quite well. My question to you, Ed, is in terms of the software, how deep can you peel the layer? Because the API seems quite nice, and I mean, it's very well designed. If what you are, but for your intended audience, which is researchers, they just want to go ahead and set up, put the settings, and then off you go. But what about if you want to peel the layers a little bit and tweak a little bit the algorithms? There are so many ways in which you can tweak what's happening under the hood. So I'm curious as the flexibility of the tool.
So I think you can do that. I think probably the documentation is probably much more user focused than developer focused on that point of like if you want to add your own algorithm or like change stuff. But basically, if you can look into the code base, or like, you know, the team is using GitHub discussions and so on. Basically, it's C++ under the hood, and there will be a way of like defining the games that I think could be, that people could add new ones in the future. Defining the algorithms for Nash computation, I meant to say. But yeah, in terms of tweaking them, it's not something that I've tried. I think at the moment, like, it's not the kinds of contribution that the core developers are like trying to invite. But having said that, like, if it's something you're interested in, I think they'll be very interested to hear about it, because they want it to be like a package that people go to for like state of the art ultimately, which at the moment, you know, they're moving in that direction, but it's obviously a small number of academic developers. So yeah, and I think they need to do some more like benchmarking and against other packages and other algorithms to do the same kind of thing as well. At the moment, the thing that's nice about it is it's just there's lots of things in the same place, like tools for doing game theory stuff. So yeah, hopefully that answers your question. I just wanted to one final point on the how it's being used for cybersecurity in particular. So some of my colleagues at Alan Turing Institute were using it, for example, for modeling like attacker behavior versus defender behavior. Again, this I think is one of those examples which comes under like writing an academic paper. I don't know whether like cybersecurity software is actually using that approach, or like how that would even make sense. But yeah, anyway, that's, yeah, I'm sure you're all familiar with the distinction between academia and reality, but you know, it overlaps.
Okay, so if you have any more questions, I encourage you to ask them like on Discord, or probably you can find that somewhere today. So now we end this talk, and in 10 minutes we'll have another one, so we can switch rooms or stay here. Okay, welcome back. Now it's time for Vasu to tell us a bit about the illusion of compliance and auditing LLM as a judge system. So please give her a huge round of applause.
Thank you. Yeah, thank you for having me. I'm Vasu Sharma. I've been working as a data scientist for close to 10 years, and today I'm going to talk about bias and fairness. So effectively, the talk is about social sciences, so some studies which have been proven in different contexts for over 50 years in social sciences, how they are getting more common, so to speak, with the advent of AI and LLMs, and how some Python tooling can help us at least detect those biases. Mitigating is definitely a separate context, and it's not just about being fair and having equal opportunities to everyone. We also have the EU AI Act, so compliance is necessary, and we need to show that the systems that we are building are not biased or discriminatory towards some specific group. So yeah, you'll leave with a mental model of what intersectionality is. It's a social science concept. We'll talk about it and how we can audit our systems. It's not necessarily about just hiring, but I use that as a main example here. Some of the Python libraries which you can use for fairness and the metrics which are there, and some unique challenges and opportunities which now we have, since not a human person is probably having these biases, but these biases are getting increased because of LLMs. So, a show of hands, who understands what LLM as a judge is? Okay, quite a few. So good. So the idea is that, for example, for hiring, most of you or some of you have at least applied for PhD positions, masters, or maybe some job. You know the concept of ATS. So there's a CV, there's a job description, and some mechanism, some algorithm checks these persons have these keywords. So let's shortlist those and so on. So this has been long been the case. But with LLMs, this gets much more easier to do for companies. So you can have an LLM, use an API, have a job description, and have the text of the CV, and just ask the LLM, please rate this person from a scale of whatever to whatever, if this is a good match or not. And you do that for every person who applies, and then you can get the top candidates, for example. This is like the simplest approach. More efficient would be if you would, for example, feed the LLM the CV and the job description. The LLM would represent each of these as a embedding, and then you can say which person's embedding is nearest to the job description, and so on. And this is just a hiring example. LLMs as a judge are being used in medical trials, credit risk, and legal exposure. And starting 2nd of August 2026, so not far off now, EU AI Act is getting, I mean, it already is there, but if you know, there are certain categories of EU AI Act. So there are some categories for which it's voluntary, for example, for recommender system and so on. And for some categories, it's prohibited. And some categories like hiring are in high risk categories. So for them, the compliance reports that you have to provide that this is not discriminatory, this and a couple of other things is quite detailed. So you have to show that your system is not discriminatory. And if they find that something's wrong, there's a fine of up to 15 million euros or 3% of your revenue, whichever is higher. And then there are some other much higher fines for the prohibited category. If you're following this discussion, you know that the digital omnibus deal earlier this year kind of asked to delay this deadline, but it's still not final yet. So we have to assume that starting next month, we have to show that whenever we have LLM as a judge in hiring or these high-risk categories, these are not discriminatory. And usually, there are approaches that people use to check if the system is fair. So imagine that you have a system, you are a company, you have collected quite a few CVs, many job positions and everything. So you know how many people, how many men applied, how many women applied, you know maybe their racial identification as well. So for example, in US, a lot of companies do ask voluntarily if someone wants to mention what their gender is, what their race is, if they have been veteran and some other categories. So usually, especially for US companies, you have this information, so you can check, this is my entire data, what is the rejection rate by gender? Yeah, 42, 37, not so good for women, but still within the tolerance. You look at the race, white, non-white. I mean, I don't like the term non-white because, yeah, different topic, because even those different races are associated with being non-white. It's like male and non-male kind of thing. So I don't like the term, but I couldn't think of a better term there. And here also you see there is higher rejection rate for non-white, but it doesn't look so bad. And if you look at the metrics, it's within the confidence interval. So you say the gap is within tolerance. So we are happy with it. All the single axis dashboards are green. So we pass the audit. However, if you look at these both axes, so race as well as gender together, so now you don't have just one category split in one side and other category split on the other side. You have all these 4 categories. You see, because maybe the non-white women are lower in numbers in terms of who applied, but if you look at the numbers, they are getting rejected at a higher rate. So even if you look, the dashboard is green, you are systematically discriminating against non-white women, which of course is not just nice for society perspective, but under EU AI Act, if, for example, a whistleblower or someone else says that this company is discriminating against this group, you have to pay a higher fees. So you have to be very careful about these going forward. Now, this concept that I talked about for race and gender is not a new concept. It's from 1989 in social sciences. They so basically this research showed that the Black women's discriminatory behavior, what they go through is not just a sum of what, for example, Black people go through compared to white people. So the negative side effects there, plus the negative side effects of being a woman. It's much worse, like I showed in the previous presentation. I mean, this study is like, you see in many different contexts that, for example, there are scholarships in US which want to promote Black women. And then there are scholarships which want to, Black folks. And there are scholarships in US where they want to promote women. And what you see is, these scholarships get to the right categories, but Black women basically are neither of those scholarships. So they are categorically getting not just the worse at one side, it's just this discrimination is not additive, it's the interaction that makes it much worse for them. So basically the outcome for them, for the unprivileged group, is not just a sum of base, and then you have the gender effect, you have a race effect, you have an extra interaction term also, which is often non-zero. So this is the race and gender, and this concept is called intersectionality. 2 things to remember here, that today, it's not just race and gender when we talk about intersectionality. There can be other sexual orientation, where you come from, which language you speak, whether you have some extra needs and so on. So they're quite a broad concept, but awareness starts at one step. And that's why at the moment I've just taken race and gender. And the second point I forgot, but I'll come back to it. Yeah. And now, since we talked about LLMs as a judge, let's think about how we can test such a system. I mean, the benefit of we having an API key is that we can do this kind of experiment on a scale. However, for a human bias, we need many non-white women to apply for a job for the experiment to have enough power, right? But for an LLM, you have a CV, you look at it. If it doesn't have some terms which kind of give away whether this person is male or female, we remove that. If the CV says that this person was part of the Boy Scouts, we remove that, to make sure that it's still fair. And then you add this information for a cross product, so to speak, and look how the LLM has been scoring these people. So basically the same CV, you annotate it with male-related information, female-related information, some black female-related information, and so on. So you have this cross, 2x2. And then you can also look how the LLMs are doing in terms of base. So there are usually some foundation models, and then the fine-tuned models. So you can also see if there are differences between the two. So this is a simple experiment that we can do to make sure that our LLMs as a judge, which does not necessarily have to do in hiring, by the way, but that's the use case I'm taking here, is fair or not. And when you do that, of course, now you have not just one metric to look at, whether the disparity score is looking okay or not. You have multiple, since we are doing cross product. So the easiest way you can still think about it is these 4 simple audit pieces. The first step is, like I said, you just don't do single axis split. You do multi-dimensional slicing, so full cross product of protected attributes, not just the marginals. Then additivity testing. This is what I talked about. With the entire data set, you have a baseline. You can find out if there is statistically significant difference for gender. So you have the gender aspect, then statistically significant term for race, and if there's an extra term. So that would be the interaction term. If you find something statistically significant there. And then heterogeneity detection. This just means that usually when you find if you have a system which is biased, so you do this test, you find that there is a bias. Now you want to improve that system. Usually if it's a tabular data, there are actually very good tabular debiasing techniques that you can use. And for LLMs, you would usually do fine tuning with new data where you want to make sure that these, the outcomes or the decisions are not biased. But even after doing that, it's good to do the same thing again. Because what happens usually, or has been happening, is that after this mitigation effect, you have one group which is looking good. So the gender gap has reduced, the race gap has reduced. But if you look again, that split, the group which was doing worse is now much worse off, usually because this is a smaller group. So since you're trying to optimize a bigger data set, you kind of look at the average, what is going to make on average the bias go down, but these people are still getting the shorter end of the stick. And this is what I was just talking about. You would have this difference. So this is the additive testing which I was telling you about. If you look at the base, and then you have the race term, you have the gender term, what would be the predicted rejection rate for the non-white women, for example? But actually, in the observed data, it's much worse. This is what you'll see as the residual. So this is a very big residual, of course, given the data set and the number of people in each category, you could see if the confidence level is good or not. But that's the main idea. You would get some, 24 point is maybe like the median of it. You would get a range of it, and you would be able to see if it's statistically significant or not. And this is the dimensional heterogeneity concept that I was explaining. So this is all just illustrative examples. So like I said, you try to do this multi-dimensional testing for bias. You found out there is a bias. You try to mitigate it. And now you want to test if after the mitigation, the problem is solved or not. Now you see, if you just look at the gender gap, it has reduced quite a bit. Top. Race gap also reduced quite a bit. Great. And then this looks like, let's do it. This is a great new model. Let's ship it. However, the harm has not just disappeared. It's just hidden now because the non-white women category is getting worse. Like I said, the model tries to optimize for the entire data set, what would be the best way to reduce the bias. But since these subgroups are anyway smaller, they get much worse now. So it's important to also make sure that even after you do the mitigation, if the data set has improved or not, you look at it. Yeah, so like I said before, with the EU AI Act, the compliance is necessary. It's not just sufficient to just do a single axis. It's also important to do this kind of audits voluntarily to make sure that if something comes up, you can show that you have done thorough bias detection studies, and you know that your system is not discriminating against any smaller group. So this would be like a very concrete, reproducible framework to make sure that we did check for gender and race. Of course, this means that if you want to add another dimension for it, whether the person had, I don't know, a different sexual orientation, or did they have some special needs and so on, this would then grow exponentially in each category. However, that's the benefit of it being an LLM as a judge. Not a human person has to go through then 10 more times or 16 more times the same CV, but the API, or like the API call, can give you the answer rather quickly. That being said, the EU AI Act requires bias testing rather broadly. So it does not specifically say that intersectionality should be considered. But even if that's not the case, I would argue that this is the right thing to do, since we want to have everyone be able to use their best of potential and not being put down by other people who get the job. Now about the Python libraries that look at fairness. So I looked at some of these here. And basically FairLearn and AI Fairness 360 are the most common ones, or like popular ones. So you can see that the GitHub stars are there. And both of them actually do consider intersectionality natively. So so basically, instead of a single sensitive column, you can mention multiple sensitive column and so on. And the new, like I think early this year already, this new Python library came up. It doesn't have a lot of GitHub stars because it's really specifically made to make sure that this use case of intersectionality is getting covered. So they have this concept called worst subgroup search. They search for, if you give all the categories, which subgroup is getting like the worst outcomes. So it's a still young project. I would still recommend for everyone to maybe have a look, since this is something that's important for me personally, and I think it should be important to everyone. One thing I still want to say about that is that this intersectionality concept is, if you know how the Python library works, you can use it, but it's not, I mean, not everyone is aware of it, not everyone cares about it. Like I said, it's usually the single axis that people think about, and no one really asks about it in the beginning. And yeah, the usage is quite easy. If you have like small enough data set, you have pandas. I don't know if they support polars. I don't think so. But at least if the data set is not big enough, which would usually be the case since you would have aggregates, not each data point, then it looks very easy. You tell which metric you want to talk about, selection rate, so yes or no, if you have that column, and you can tell the judge decisions in yPredict. The interesting thing is that there are multiple metrics that you look at. If you just want to look at the selection rate, it's okay to have these race and gender features, which are the sensitive features here, and the judge decisions. But if you have some human person also having if this CV should have been selected or not, then you can also provide y true as y, and you get kind of metrics which are error related. So the LLM as a judge made an error in this case or not. And eventually you get like overall for each category, like a group for every intersection, one row. You can also have a look at how many number of people are there in that group. So if maybe just 10 are there, you know there's not enough power for this test, you can not confidently say anything about that subgroup. And you, with this MF difference function, you basically compare everyone else with this worst case gap, which is what you look at when you look at the disparity ratio. Yeah, and effectively, that's my talk. If you want to remember anything from the talk, I just want to remind you that scale is a multiplier. It's a different game altogether when a human recruiter who's biased, because all of us are biased, of course, are making decisions, maybe hundreds. And then you have a model which is capable of doing these decisions in minutes and maybe is making millions of decisions. And we have in our community, in our society, groups which are anyway, not so privileged, and we are giving them not enough opportunity to use their full potential. Second important thing is if we have just single axis metrics, these are not enough because they hide these intersectional biases, which might be harmful for some subgroups of people. So you can look at, I mean, especially when people's lives are at stake here, the averages looks green, but you still care about the people, and then you have to be really thorough and sure that you're not discriminating. And the last point is that these LLM as a judge system is applicable everywhere. I mean, the framework, so you can still call API for credit risk decisions and so on. It's a very generic framework. Since the faking the demographics is pretty cheap, I mean, you have to pay for the API calls, but it's much cheaper than a human having to say if it gets rejected or not. And there's maybe a fourth point, which I said before already, that intersectionality is not necessarily just the gender and the race, although that's how it started. It's much more, and we want to be an inclusive society overall, irrespective of where someone comes from, which language they speak, and so on. So the solution is still, I mean, no matter how many sensitive attributes you take for people, it will never be perfect, of course. But we definitely should try our best, and that's what I hope you take home. Oh, this was just an example, and thank you so much.
Okay, thank you. And do you have any questions? Please raise your hand.
Thank you very much for your talk. I have one question. Early in your talk, you you showed that the rejection rate between male and female, there is an acceptable gap. So my question is, who defines that gap? And is it like a fixed or a dynamic value depending on, what is the percentage we are seeing?
Yeah, thanks for your question. Actually, it's a fixed value. It's like, for statistically significance, the community has accepted 95% confidence, and it's similar here. You try to see what the worst case. So the best category, let's say white men, how much selection rate they have, and if the selection rate of any other group is worse than 80% of that, then it's called worse. Otherwise, it's within the tolerance. So this 80% for disparity ratio is the norm, essentially.
Okay, do we have other questions? Okay, I don't see any. So maybe if a question pops up, you can probably ask on Discord, or he'll probably be somewhere out there. Okay, so thank you again, and please, a huge round of applause. Okay, welcome back to the next talk. This will be BioCabinet end-to-end agentic workflow for omics. So please give a huge round of applause.
So, hi, and thank you for attending the talk. And my name is Ishita, and I'm a PhD student. So, computation is difficult, and so is biology. But then who wants a simple life, you know? So, I decided to be at the intersection. So, I do both. I am also a biologist, and I'm also a person who deals with computation on a daily basis. Now, before I start with why BioCabinet, I want to start with what is the need of developing one more tool when you have hundreds and hundreds of them already? And those scientists are definitely the brilliant ones. I'm nothing in front of them. So, yeah. So, since 2000, the modalities of the sequencing has increased exponentially. From 2000, we already had just bulk RNA sequencing. Then in 2009, single cell RNA sequencing came, and 2016, spatial transcriptomics came. And what's surprising is none of them replaced each other. They complemented each other. That's the beauty of it. But with each and every modality, what also came was difficulty for every scientist out there, because they have to now make more judgment calls to actually make sense out of data. Otherwise, it's just hundreds of tables and thousands of matrices, and you are just stuck there. And our scientists were no behind because the number of tools have also increased, like DSeq2 for bulk analysis, SquidPy for spatial, and then ScanPy for single cell. So, and we also have this whole SC-verse for the spatial and single cell analysis. So our scientists was no behind in actually making sense out of the data. But it is difficult for the wet lab biologists to have to manage both. And I have spent like 3 years working with them. So I decided to build BioCabinet. Now what this does is, it has an orchestrator which actually determines that what kind of data are we dealing with, whether it's spatial, it's single cell, it's bulk. And it is complemented with an LLM at top with the orchestrator node. Then, on the basis of that, it actually orchestrates the whole pipeline for you. And here, exactly here, at the RAG layer, you just get the summary. Why? Because wet lab biologists have a lot of work to do. They just don't want to sit at the screen and make the quality control calls. So why not the LLM do that? Now, you might be actually wondering that what is LLM gating? Okay, so it's not an established term. It's what I call it. So I will explain it now. But before that, I want to actually emphasize that I'm not a person who has built a lot of packages or who has a lot of experience. But my theory of building the package started with compute, decide, and check. Compute. Use Python to extract the numbers because numbers don't lie. They are concrete. Then decide. Here we have an LLM who will decide that does this call make any sense, or you have to make this call at all in the first place. Check, because your LLM can hallucinate. And in this process, I have had so many instances when LLM did something crap and I have to have a hard fallback for that. So always check. Also, if I tell a biologist that I'm not going to check what the LLM is doing, they probably won't even use it because it determines the sum of their coming weeks of experiments. Now, let's see what LLM gating is. Okay, so we start with the quality checks and we extract all the matrices which are required over there. Now, what happens is we want to decide for each and every sample that do we want to do this quality check or the sample is fine and what kind of quality check is required. So at that point of time, we call in the LLM. If the sample is failed, the sample is already flagged. So you don't waste your computational resources in processing a bad sample at all. And then if the sample is actually having a good quality and just needs some trimming or just needs some processing, so at that point of time, here we call the LLM. Now this LLM here will actually decide the parameters for each and every sample. Now the question is, why each sample? Because each and every sample is processed by a different person in a different lab, maybe if you're having multiple batches, or maybe by different experimentalists, and different hands, different errors, and different kind of way that you have processed the data in the wet lab. So that's why we have this for per sample, and then you do the parameter validation. So your LLM is not giving some crap parameters which does not make any sense. So at that point of time, if it is giving a validated, yeah, the parameters are fine according to how the tool was made, then we start the trimming. Else we have a hard-coded fallback, and the user is actually told that, okay, the LLM did not give the parameters and this is the hard-coded fallback. Do you want to proceed or not? Just to have the human in the loop, which I think is very much important. Then again, we want to talk about an interesting part, which is actually the most important for me as well, because I have spent 2 years just looking for files and making pathways by myself, which is the graph neural network for protein-protein interactions. Now, we have so many. Why do we need one more? Here. So we have this string database, which is a protein-protein interaction network. How do we do that now? So the first path we talk about, we take the ESM2 embeddings. This is from Meta. And then I use a BioBot model to actually embed each and every pathway embedding to these already produced embeddings by ESM2. Yeah, we can argue that it's by Meta, it's ESM2 embeddings. Why do we need more? But I think that as a biologist, when I used only meta embeddings, it did not make much sense for me when I saw the results just with ESM in training the graph neural network. So my precision and my recall were both very low. Could have been my mistake, but I think that when I added the BioBot embeddings to them, the results were pretty good. Then you concat them, because the ESM2 embeddings and the BioBot embeddings together are 768 dimensional. So we come down to 256 dimensions. And then we use them as node features. And these nodes come from already present data. That is our training data that we have from the string database to build this graph isomorphism network. Now, this is a question that I also had, that why do I use graph isomorphism or a graph convolutional network? Because graph isomorphism network makes sure it does not take an average of all the neighbors. It takes a sum. So it is not influenced by the outliers, which is very important, because otherwise the node embeddings are influenced by the outlier, because in mean we have this problem. And then we have the edge prediction head. So you have 7 kind of edges that we can have: binding, activation, inhibition, regulation, expression, and the post-transcriptional modification. I said in the starting, biology is not easy, right? So that's why that is reflected in the computation. So that's why we have a sigmoid, because you have probability for each and every class. Now I know I have said a lot, so I want to show you something. So maybe that will make things more clear. Okay, what the hell is that? Okay. Yeah. So this is just something I made using Manim to just show how it actually works. So we have all our proteins here, and these all proteins have their embeddings, which are the embeddings using ESM and also along with the BioBot. And they are all the neighbors of this protein A, and they are concated. When I say concated, they are added, not averaged. And then it knows all its neighborhood. In one pass, it knows its neighborhood. In 2 pass, it knows neighbors of neighbors. So that is how we do it. And then we have 7 interaction logits that come, that we discussed in the interactions. And then we have a logit loss, which is calculated. And that is why we call it the protein-protein interaction network using the graph neural networks. And now I want to come to this layer, that is the RAG. So actually, I want to go, give you a bit of background over here, that why RAG actually. So you can have all these pipelines in R and Python, but the problem with these pipelines is that you have to go through tons of files. If I'm looking for one pathway, I don't want to open 5 files and see, okay, this gene is there or not. So here is RAG. Now RAG has all the information from all the pipelines that have run, all the states. It has everything. along with the pathway information from KEGG, Reactome, and Wiki pathways. And they are encoded using the same bioword, just to be in the same space of the transformer which was used for the embedding. And I have implemented all these tools, and the LLM can pretty much make the call by itself, that which tool it actually wants depending upon the user query. The user query is actually decided by the cosine similarity. Like if you are asking for a pathway, so it will pretty much do a cosine similarity research in the documents, and then it will give you. But if your question is somewhat different, which is not actually given by any of these tools, then it can pretty much do the web search and get you what you are looking for. And this is the converging point for each and every analysis you do, whether it's single cell, whether it's spatial, whether it's bulk, because in every of the analysis, you will get the genes or the markers you are looking for. And now this is the kind of agentic loop that I designed. Now I want to start with telling that I designed it completely wrong in the starting. I had 700 lines of code, a brittle logic, looking for keyword matching, and because I was very skeptical that what if LLM is giving crap at the end? And I was like, no, this doesn't make sense. Maybe I'll just hard code the logic. But trust me, with this logic, I cannot actually expand the vision that I'm looking for. If let's say you are looking for a repair pathway and I want to connect it to something else, it wouldn't be giving you, because this is very limited. So that's why I designed this. Now there are no brittle logics or no breakdowns. LLM, he's the person who is actually automating everything. I will say it is a person because at the end I have asked crap questions to this RAG and asked anything just to test what is happening over here. So yes, that is what happens at the end. And yeah, so, you know, like we need to benchmark. I can't tell a biologist go and use this tool and trust what it is saying. Then I used it on the single cell RNA-seq benchmark, which is the PBMC dataset, which is one of the most easiest dataset to deal with in terms of the memory as well. And it performed pretty well in both in terms of timing and terms of the ground truth and what I get using the pipeline. And this is GNN PPI benchmark. I used a dataset which was a ground truth, which I know. This was the benchmark, so I used it, and I know the precision here is quite low because it is predicting quite some amount of false positives over here, but I'm still working on it. And yeah, because I think here, in case of test 3, it still has a high recall, but the precision is very low because in this, it has both the proteins unseen. So there are 3 test buckets. Test 1, both the proteins are seen in the training set. Test 2 bucket, one of them is seen. Test 3, both of them are unseen. So to test the generalizability of the test. And both the modalities were validated against the ground truth, but still this part needs some more work to be done. And now a major problem that you face, that if your pipeline stopped in between and it crashed, that is something that I have faced and most of the people working in bioinformatics have faced. You have to go on from the starting. Computational resources wasted, time wasted, a lot of headache after that. So basically it's built on land graph architecture. So basically we save everything in the database and you can resume from where your pipeline crashed. I think this is the best feature because my pipelines have crashed for the first year of my PhD like anything. Because I was using Nextflow, and if my laptop got switched off or something happened, they always crashed. So yes, so that's why I deliberately put this feature in there. And even if you give a thread ID or not, the child will always derive the thread ID from the thread ID of the orchestrator. So you can always go and check where your pipeline crashed. And the future work, which I mean, I'm still working on. I need more benchmarks. But now I don't want to benchmark by myself by some data sets. I would actually ask biologists to do that benchmarking because every data is different in biology. And the biologist itself, when they look at the data, can tell that how is the pipeline performing for them. I want to include more modalities of data like imaging data and more types of sequencing like ATAC-seq, ChIP-seq. There are so many now. Higher precision, which I just mentioned, because The recall is fine, but it is predicting more false positives and including more data for the RAG, like having more and more documents there, more information there, maybe more literature search over there. So yes, this is the future work that is still yet to be done. Although the first version is available on PyPy, you can just go and check. And thank you. And this is my LinkedIn, so yeah.
Okay, we have a few minutes for questions. If you have any, please raise your hand.
Yeah, thank you so much for the talk. I'm very impressed about like the breadth of all the different bioinformatics tasks you're doing, because I think a lot of the time, you know, the protein science is kind of its own field, the single cell its own field, and then the bulk is its own field. So it's quite impressive that you kind of connecting all of these different modalities. I'm curious for, because you mentioned that as a human, you also want to be able to check and make sure that whatever the, you know, the agents tell you is accurate or makes sense to run. Do you have like an example or where like how this works and how you do that, and to what extent the user has control over whatever?
I mean, the user is required in the starting. For example, when you are dealing with the RNA sequencing, it will ask you for your references and for your FASTQ files in the folders itself. It will only ask for the human in the loop when it has flagged a sample, and it wants to ask you that I am stopping the processing of the sample and I'm flagging it, and then it just kind of informs you. And if in case you really want to process it, even if it is after flagged, then you are in the loop. That's it.
See, so does that mean that the types of workflows that you can do or that the LLM has access to are quite fixed? So, for example, the sequencing workflow has to be like these and these steps, and they either decide, you know, for each instance if that continues or not, or does your system allow like more complex decisions to say like, oh, based on this, I want to do a very different workflow for a certain sample or data set than for another one?
So right now the LLM which is at the RAG level has access to everything. But when I have multiple pipelines and they are independent of each other, at that point of time, LLM only has the access to what it has done in the previous nodes and not what it is going to do in the nodes are coming after that. And I have not given LLM that kind of capability right now to take all the decisions by itself, because sometimes the decisions can be very complex and it can go completely wrong way. So there has to be multiple fallbacks that has to be coded still. So right now it has access to only the information for the nodes processed above it.
I see. Thank you.
Yeah.
Okay, do we have more questions? Okay, I don't see any, so thank you again, and round of applause. Hello, hello. Yeah, please keep it like kind of close to your mouse.
Hello, hello, hello. Fine.
I'll be using this one. One. Okay, welcome back. Now our next speaker will be Akshita, and she'll tell us about unpacking parallelizing network X algorithms. So please give her a huge round of applause.
So hi everyone. Today I'm going to be, like you mentioned, discussing unpacking parallelizing network X algorithms. So before I begin, I'm a student. I'm an undergraduate student. I'm studying third year of my BTech in computer science, and I'm from Indian Institute of Information Technology, Gwalior from India. And previously, I've contributed to NX Parallel, for which I'm a co-developer and maintainer, and also NetworkX. And whatever I'm going to be discussing right now is a part of my Google Summer of Code project. So have you ever run into a program, you've watched it take longer than it expected, and you open up your system monitor and you're like, you notice only that one of the core is completely busy and the other 7 or 15 that you have are just sitting there doing nothing. And you're wondering, like, I paid for all of these cores, why aren't they working? So today I'm going to be answering that specific question through the lens of graph algorithms. Specifically, we'll look at how we can make NetworkX algorithms take advantage of modern multi-core systems through NX parallel. So most of you might already know but in case anyone who doesn't know what a graph is, so these are a few real world examples of like road networks, flight network, and social networks. So road networks connect cities, flights connect certain destinations, social networks connect users. And so graphs are basically a visual representation of entities and the relationships between them. So these entities are called nodes and the relationships are called edges. So how are these networks used in the real world? So usually we have questions that we want to answer, like which of the following node is most influential, which communities exist in this network, or what is the shortest path between two different destinations, like you can see over here. This is where network X comes into picture. So network X is one of the most widely used Python libraries for graph analysis because it provides a simple interface for building graphs and running sophisticated algorithms. With just few lines of Python, users can analyze networks that would otherwise require implementing really complex algorithms from scratch. This is just a small example of one use case of network X where you can just add in any graphs and you can just print a number of nodes. But the main issue comes when, so for small nodes, small graphs which have a certain less number of nodes, let's say 10 to 20, all of the algorithms that you run come up and give results in like seconds. But the issue comes in real world scenarios where social networks contain millions of users and transportation contain millions of connections. And these algorithms that once take seconds now take hours and minutes. So as these graphs grow, we come back to our original question, which is, can we simply use all the CPU cores in our system to make these algorithms faster? The answer is that not always, because parallelism mainly depends on the structure of the computation. Some problems can be divided into independent pieces. So let's say grading 100 different exam papers, like each subject can be taken by a different professor and all of the results can be compiled in the end. And in other cases, like baking a cake, you obviously can't decorate it before baking the entire cake. So each step in certain cases depends on the previous step, and graph algorithms work in a similar way. So for example, we can compute, let's say, shortest paths from source node A is independent of the shortest path computation for source node B. So these computations do not really depend on each other, so they can run simultaneously on different CPU cores and the results can be combined at the end. Such type of algorithms are called embarrassingly parallel algorithms, but there's nothing really embarrassing about them. So not every algorithm has this specific property. So algorithms like depth first search or breadth first search that you might be knowing are sequential by nature. So such algorithms cannot really essentially be parallelized right now by NX parallel. So it focuses on those algorithms which are embarrassingly parallel. So how does one algorithm go from a network X algorithm to an NX parallel algorithm? We have a dispatching mechanism in place for network X, wherein any algorithm that is specifically invoked by the user hits the NX parallel backend as specified. And if the user is using, if they want to use, if that specific algorithm exists in NX parallel, we use the NX parallel version. If not, we depend directly on the network X sequential version, but the API is identical and you get the same output. So this is one way in which you can invoke parallelism via NX parallel. So you can run your script that you wrote and export the automatic backend as parallel, and then whatever code, that algorithm that exists in your code file runs the NX parallel version directly if the implementation exists. If not, it falls back to the sequential version. Another way is directly passing a parallel graph object. So you can define a specific graph object in network X directly, and so parallel graph object is just a wrapper around this graph, and you can pass that for any algorithm that you want to run. So betweenness centrality exists both in network X and NX parallel. So I've taken this as an example. Another way is you can take the argument, keyword argument backend, and you can pass in parallel, and that specific algorithm invokes the parallel version. one other method is if you want to directly interact with the NX parallel library, you can directly call betweenness centrality from the existing library itself, or you can make another parallel graph object like we discussed earlier to interact directly with NX parallel. So how does this flow work behind the scenes? So what happens in NX parallel? You basically partition your set of nodes that you have for that specific graph and break them into specific chunks. And we depend on joblib, which distributes this computation across multiple CPU cores. And this runs independently on each of these workers. And whatever results that we get from individual computation of nodes at the end is merged into a final result, and then it's returned. So a small example for you to understand better is, let's say you have an input graph node and you're performing a computation on 20 of those nodes. We split it into 4 equal chunks if you want them to run on 4 workers, and each chunk is dispatched to a specific worker, and that particular worker takes care of the nodes in that chunk alone, and the results that have been generated at the end are combined and the merged final output is presented to the user. But parallelism also comes at a cost. It is not free. While we gain performance by distributing computation across multiple workers, creating and coordinating these workers also introduces additional costs. These costs have generally 5 categories in NX parallel. The first would be computation. So this is the actual work that we want to parallelize, the algorithm itself. So parallelism only helps if the computation is large enough compared to the overhead. You can't just run a for loop that's summing different elements and try to parallelize it, because then the overhead would dominate and you won't see any benefit of parallelism, which is our performance. Then the second is serialization. Before data can be sent to another process, it needs to be converted into a transferable format. So for graph algorithms, this often involves pickling and transferring the graph data to each of the worker. So if the graph is containing multiple nodes, then serializing and pickling that graph object to individual workers adds some additional cost and time. The third is process startup. So creating worker processes is not just instantaneous. So there's some amount of time that is spent spawning and initializing workers that contributes to the overall cost. And the next is scheduling. So once the workers are already started, tasks need to be divided and assigned efficiently. So libraries like joblib handle this coordination, but this also induces overhead for us. And finally, this is one extra step that we do in NX parallel, which is merging, which is not required in the sequential version. But since each worker does the computation independently, we are required to merge it at the end to give a finalized output. So the benefit of parallelism depends on the balance between these useful computations and these additional costs. So if the computation is large and independent enough, the speed up then outweighs the overhead. But for smaller problems, the overhead really dominates. So one of the biggest sources of overhead is memory, and graph algorithms often need access to graph data throughout the computation. So one simple approach that we follow here, one simple approach would be creating separate copies of the graph for each of the workers. So let's say you have a graph which has 2,000 or 3,000 nodes. That would mean you're creating a copy of the entire graph for each independent worker, which is really wasteful if the graph is just being read. So so we have, let's say, 4 different workers here. And for small graphs, this is acceptable. But for large graphs, this becomes really expensive. Memory usage increases and startup time also increases. And a lot of time is usually just spent moving data around instead of doing the actual computation. So to reduce this overhead, NX parallel uses memory mapping techniques that is provided by joblib for NumPy arrays. So we convert the graph object to existing NumPy backed graph representations. And instead of repeatedly copying, we dump this graph into a file that is accessible by each of the worker. And once the object is accessed by the worker, it doesn't really have to copy. We share the file path, or wherever the graph is stored, the location is shared to each of the worker, and it directly accesses the graph. So another thing is that if the user is unaware of the potential inefficiencies of running NX parallel algorithms on small graphs, it's really our job to take care of how and when we want to invoke NX parallel as well. So let's say the graph, an algorithm is being run for just 10 nodes. In that case, NX parallel is really wasteful and the user needs to be pushed back to the network access sequential implementation. So in that case, we have a should run decorator that wraps each of our NX parallel function, which prevents the algorithm from being run via NX parallel and resorting back to the sequential version. So if the workers are not enough or the computation is not enough or the size is really small, we go back to the network X version. So certain trade-offs that we see here is that for small graphs, like I've mentioned, the overhead really outweighs the benefits. And for large graphs, you definitely see significant speedups. For dense graphs, it's usually definitely faster based on the edge probabilities that you have. And sparse graphs, it's really unpredictable and it depends on how the edges have been represented in the graph itself. So this is a heat map that we have generated from our timing script. So each cell you have on the left side a parallel runtime and the right side is a speed up that you get. So on the left side, coming to this specific one for 1600 vertices in a specific graph and the edge probability one, you see that the clustering algorithm, which is run on 8 cores, as you can see over here, takes about 19 seconds and this is in NX parallel. But if we resort to the existing sequential version, we take about 70 seconds. So NX parallel gives about 4x benefit. You might also wonder that if we are running this on 8 cores, why isn't it giving 8x speed up? That's because of all the initial reasons that we discussed about parallelism not being free. So yeah, so as you can see, with growing number and the edge probabilities, you see that the amount of speed up is also increasing. And a few other set of observations that I discovered during the process itself. Some of the NetworkX algorithms really give out generators. These generators cannot usually be pickled across workers. So what we do is we consume the generators in worker itself, and then we merge the results at the end. And it also matters as to how much chunk size that you select, because small chunks really improve the load balancing, but it adds up to increasing scheduled overhead. But large chunks reduce the overhead, but leave these workers underutilized. So chunk size must really balance parallel efficiency and task management cost. So coming back to where we started with why isn't my graph algorithm using all my cores? Hopefully the answer is a lot clearer now. And the reason is that effective parallelism depends on the structure of computation. Some algorithms naturally contain independent work, and others have dependencies that make execution via joblib really difficult. So even when an algorithm is parallelized, we need to consider the cost of creating workers, moving data, and coordinating the execution, and that is mainly the philosophy behind NX parallel. It does not try to parallelize everything. So the goal was to help NetworkX scale better as the graph data sets grow, because improving scientific Python is not only about creating new algorithms, it's also about helping tools researchers already rely on or work on better hardware. So that is my motivation behind NX parallel. Thank you so much. Thank you for your attention.
Okay, thank you. Do we have any questions? We have some time. Yes, we have some.
Yes. Thank you for the talk. It was interesting. I have a question. Maybe I did not catch it, but what kind of problem were you trying to solve in terms of graphs? I mean, was it scheduling? Was it...
So what we're trying to solve is for existing algorithms which take up a lot of time running via the sequential method, and if they can be split into computations that is done per node, we want to be able to run and utilize all the cores on the user system and run it faster and reduce the performance time that it takes if they are embarrassingly parallel via NX parallel.
What kind of algorithm?
Like betweenness centrality, clustering, like triangles, algorithms where you want to find out a node, let's say one node, which is you want to know whether that node is a part of a shortest path between n number of shortest paths. So certain type of algorithms that are embarrassingly parallel, any of those.
And for the table that you showed us, the color map, I mean, which algorithm did you test?
It's called the clustering algorithm.
Okay, yes, thanks you.
Yeah.
Okay.
Are there other algorithms in Network X which are not embarrassingly parallel, which have dependencies? And if so, what would be the approach need to be taken to balance these, workloads?
So right now it only NX parallel only. So Network X does have a lot of other sequential algorithms, like I mentioned, like DFS and BFS. Right now NX parallel does not accommodate these algorithms, and right now some amount of research needs to be done as to how we can run sequential algorithm across cores, maybe having some inter-process communication, but that would also induce overhead. So the trade-offs really need to be weighed, and only then we can decide so what a good approach is.
Thank you.
I mean, I guess because it's embarrassingly parallel, it doesn't matter how you chunk up. So if you go 4 chunks, it really doesn't matter how you split the nodes up. You don't have to think about neighbors or anything like that. It's always the same.
Yeah.
I guess I answered it.
Okay.
Maybe one last question about the chunking. So is it always done, by nodes and not, for example, edges? For some algorithm, maybe we need to split by edges.
So right now it's only done as per the nodes. So we haven't really found any specific algorithm right now that needs to be chunked based upon the edges, because nodes tend to give out a reasonable good enough result. So in case maybe we come across where chunking would be more beneficial via the nodes, we're happy to explore that.
Thank you.
Okay, if you have more questions, you can ask probably afterwards. And again, please have a huge round of applause. that's it. What else? Yeah, just explain the cards.
Okay.
So do you want Q&A session? Open. Okay, that's perfectly fine. Then you can maybe people ask questions on the Discord or something. Or, yeah, I know. It's 20. Yes. So no questions.
Okay.
So no questions and answers afterwards. So yeah.
So on 15 minutes, I
Yeah,
will show
after,
this file.
After 15 minutes, she will show this one, then this one. And then you can encourage questions to be asked on Discord or approach directly.
Okay, so I said questions can be questioned on Discord. Which channel?
I probably the room channel or.
Okay, no need to mention that.
I think you can write on Discord. There's no like there's no like forms or official way. We need only you to write on Discord so you can estimate how many people will be. You don't have any questions, I'll be available on Discord. So okay, yes. So good luck. Bye. Bye.
Just before it starts, it should be on the screen. So I say your title and yes.
But if you want to know my name, you can
It's
just
Mohammed.
Okay.
Okay.
Do we close it or no? Hello, everyone. Hello. So we're gonna have now a talk about lessons from building a large-scale engineering simulation data processing library with Mohammed. Let's welcome him.
I think it's okay now.
Okay.
Good afternoon, everyone. This is my first talk ever at any Python conference. I attended last year's EuroSciPy, where I learned a lot from various talks by various speakers, and I hope you are able to learn something from me today. So I am part of a team that helps maintain a performant open source Python library for the pre-processing and post-processing of engineering simulation data related to multiphysics finite element analysis. A little bit more about the library later on. And today I wanted to share some lessons we've learned over the years in the hopes that you find them useful in the maintenance and development of your libraries. A little bit more about myself. I am Mohammed. I work as a research and development engineer at ANSYS, where I mostly focus on contributing to open source Python packages. My background is in civil engineering and computational mechanics, and I like to dabble into football, play video games, and very light flow exercises. So this is a 15-minute talk, I hope, and that is nowhere near enough time to go into much technical detail. So I've structured this talk to be fairly light, which I think is an approach that strikes a good pedantic balance given the time. I will start by telling you a little bit more about the library I mentioned earlier by DPF Core. And the reason for doing that is to set some context so you, the audience, can start drawing some mental analogy between the library and maybe a library that you already maintain or one in which you envision to develop in the long run. And my hope is that by doing that, you are better able to appreciate the significance of some of the challenges we have faced and are actually still facing as the library evolves, and that you find the approach we've taken to address some of them useful for your use case. So ANSYS as a company has numerous product offerings. Some of you may be familiar with ANSYS, and most of these products have specialized domains. So you can think structures, thermal, optics, electronics, the list goes on. These are different physics, right? And as you would expect, the physical differences are sometimes reflected in how each of these products model their data. This difference in data modeling can sometimes introduce a little bit of friction when you have to set up multi-physics workflows across multiple products, or when you have to process simulation results coming from multiple products. One analogy I would like you to keep in mind at this stage is to think of these different products as the different consumers or users of your hypothetical library. They are going to have different data modeling tastes and preferences, which you have little to no control over. So back to DPF, the data processing framework was designed to be physics agnostic, so it addresses this heterogeneity of data, which I just described. Furthermore, it was written in C++ to be performant because simulation data can sometimes run into hundreds of gigabytes, and this needs to be processed very fast. Of course, the analogy in this case is that you want your library to be fast, so you write the part that does the heavy lifting in a performant language like C++. And PyDPF core is then the Python client library for DPF. I call it a client library because it supports inter-process communication. So communication over the network is possible. You can have the Python installation on one machine, the C++ part on some other machine, and things work essentially the same. Of course, the relevant analogy in this case is that you've written the core logic of your library in C++, you would like to have a Python interface for it. Whether or not you desire a client-server architecture is a matter of choice, and it's not all that relevant to my goal for this talk. And finally, which is the most important, is that the Python client library is cleanly decoupled from the C++ implementation. So we, as open source maintainers, are able to independently evolve the Python side of things without worrying about what is going on the C++ side. We are able to add whatever abstractions that we want without caring too much about what is going on the C++ side. So to summarize all I've mentioned so far, you have data coming from various sources in various representations. You probably want to pity the Microsoft Excel guys over there as well. It's a valid format. And of course, you homogenize this data in some way in your library. Your library does what it is supposed to do. And of course, you have a Python interface to actually use the library. So more analogies. We all know how complicated transforming data can sometimes get. One very simple example that I have, which I think everybody would be able to relate with, is that have you ever tried to understand advanced NumPy array broadcasting rules? Everybody in this room is probably way smarter than I am, but that was me the very first time I tried to do so. So transforming simulation data can even get more complicated than that, because it's a bunch of math, linear algebra, and some customized algorithms. The key idea is that the problem your library is going to solve will have some inherent complexity, and you want to design your library in such a way that managing and handling that complexity is easy. A core philosophy in DPF, for example, is to think of data processing in terms of operators that you can chain together to form more complicated workflows. And this is not a unique philosophy. You see it everywhere. If you are familiar with the visualization toolkit, for example, it's essentially the same thing when it comes to VTK algorithms and pipelines. So having set that context, I can breeze through the challenges, since I've hinted at some of them earlier. So like I said, your library would have to support data in various formats, in various representations, and you absolutely do not want to mix the complexity related to that with the core logic of your library. And you want to decouple the Python interface to your library from the C++ implementation, and you potentially want to extend your reach to even more people by exposing your library in multiple languages. One quick story I wanted to share here. So my bachelor's was in Nigeria, and then I came to Europe for my master's, and my master's took me through multiple universities across multiple countries. But in all of these universities, one thing I noticed is that the professors, whenever they want us to do any program-related project, for whatever reason, they want it in MATLAB every single time. So the moral of my story is that if you want university professors to use your library, you should support MATLAB as well. Of course, you want some flexibility built into your library so that you can easily maintain it in the long run. And I would give some tips regarding performance considerations, some tips regarding how you can manage a growing API surface on the implementation side automatically on the Python side of things. Of course, you can ship your library without any visualization capabilities built in but then nobody is going to use it, especially even the MATLAB guys as well. And of course, I would also share some tips regarding how you can maintain a good documentation, automating things via continuous integration and things like that. So on to the lessons. How do you address this heterogeneous data representation and source challenge? Well, it is highly recommended that you guard the internals of your library from the outside world, right? Otherwise, external chaos is going to keep compounding the complexity of your own library. Otherwise, you would have to consider X different data representations in different parts of your library, and that would quickly lead to spaghetti, hard to understand, difficult to maintain code. So the solution to this is to turn to our good old friend, which is abstraction. A unified data model can help guard your library against external noise. Whatever format the incoming external data is, you try to convert that to a unified data model first before you then proceed to do whatever it is your library needs to do. Of course, the form this unified data model would take depends on the context, depends on the kind of processing your library needs to do and things like that. But one very good place to start is to think about what foundational structure the data your library needs to process must have before your library can do its job. And then let that guide the design of your abstraction. So in DPF, for example, we knew that the data that is going to be processed is related to finite element analysis results. So the abstraction that we went for, which is called a field, is simply a data structure that embodies what you would typically expect from a finite element analysis, including the actual data that we want to process, which can be scalars or vectors or even tensors, and then some mesh information to add some structure and topology to that data, some temporal information, and a bunch of other metadata. So your data model becomes self-describing, making it agnostic, essentially. So to really get a feel and appreciate how we solved these two challenges, I think we need to consider the challenge in a bit more detail. And I'm sorry, I'm also going to mention things relating to ABI. I've been hearing that term since last week's EuroPython and even in EuroSciPy. I know that people are probably tired of hearing it. But like, the key idea is that when you are developing in a compiled language like C++, you hear this saying that, oh, you need to keep your ABI stable so that you don't break things for your consumers. And it is even truer for C++ than C, because C++ does not have a single universally agreed upon ABI. But what is this ABI thing? I find personally I find that the formal definition gives me a headache. So I would share like a very good mental model that has worked for me. Let us consider an analogy with the API in the case of compiled languages. Suppose you are the consumer of a library, right? You consume a subset of that library's API. If there is any change to that library, as long as the API subset that you consume is not directly affected, in most cases, you can usually just update the version of that library. Life goes on, your code is not broken. Emphasis on in most cases. But in the case of compiled languages, things are usually a bit more tricky, because a typical compiled package is distributed as the combination of some binary and some header file containing the API definition. You as the client, you program against that. It can be that you're writing a Python extension module, for example, or you're even writing your client code in a compiled language like C++. The key thing is that at some point you have to compile your own code as well against that binary. The ABI is then this implicit contract between the binary resulting from the compilation of your own code and the upstream library's binary. Okay. And when they say ABI compatible change, it simply means you are able to switch the upstream library's binary for a newer version without the need to go through this compilation process for your code. But like I said, things are finicky in the C++ world. Changes that would normally not have resulted in a breaking change in the case of the interpreted case can break things in this case. Non-client facing changes, internal library changes can easily break things. And that results in this coupling that I already mentioned, making it very difficult for you to make changes. So the key takeaway is that think of interface in the compiled case as a combination of the API and the ABI, and that maintaining a stable ABI can prevent decoupling if not handled properly. So I've been giving you bad news. Now it's time for good news. How do you address these two challenges? So there is this very nice pattern called the hourglass interface pattern. And the fundamental idea is very simple. Rather than expose a C++ API directly, you instead expose a very thin C API on top of your C++ implementation. Then any client-facing API that you want to actually distribute should be built on top of that. And this actually addresses those two challenges. You're more or less killing two birds with one stone. And the reason for that is that C has a very stable and almost universal ABI. And almost every single language in existence today has some form of foreign function interface mechanism for calling C functions, including JavaScript, including MATLAB. Of course, in the case of Python, you can use the C types module, or you can use CFFI. So like I said at the beginning, the duration of this talk is not enough to do justice to the technical details involved. I don't even think I can do justice to it anyway. So I invite the audience to watch this C++ conference talk on Hourglass Interface by Stefanos Dutoit. It's a very interesting talk. So I'm running out of time. I won't dwell much on this other than that to say that on the Python side of your library, you might want to consider things like caching and lazy evaluations. That is really going to help if you have to process large amounts of data, especially when you want to support something like a client-server architecture. Also, as the API surface of your library grows and you keep exposing them on the Python side, there are eventually going to be repeating patterns, and writing some of the code essentially becomes boilerplate. Rather than just doing things manually, there's a very smart thing that you can do. So you can have a bunch of your API on the implementation side, whose purpose is just to introspect implementation side objects and provide information about them. So what you can then do is to combine that information with a template engine like Jinja to generate all of this boilerplate code. Of course, there are other options. I'm running out of time. Can I get 2 more minutes? So, of course, there are other options. Jinja is not the only option available. For example, we use Mustache, and if you check the PyDPF core code base, we have about 1,000 modules that are actually being generated this way. And so for the visualization side of things, in our case, we went for PyVista, for 3D visualizations. There are a lot more options. This is opinionated. You have other libraries that you can use to accomplish the same case. It depends on what works for you. And as for 2D visualization, there are a lot of options available as well. Matplotlib, Seaborn, Plotly, the typical go-tos. For the documentation, I recommend the Sphinx ecosystem. Of course, there are other ecosystems like Micdocs, which is gaining increasing popularity. But the Sphinx ecosystem is very matured. If you want a beautiful documentation, there are a lot of themes available. If you want to automatically generate your API documentation from your doc strings, there are extensions available for that. If you want to automate the generation of your examples, there are extension modules available for that. So the possibilities are really limitless when it comes to the Sphinx ecosystem. And finally, to wrap everything up, how do you ensure that your library is maintainable in the long run? Well, by doing a bit of everything I already mentioned. And the most important thing, if you take nothing else away from this talk, is that in the process of eliminating complexity via abstractions, you should try to get that abstraction right, because some kind of abstraction can do more harm than good. And of course, even if it means you have to write more code, you should write more code to keep things simple. And specifically for data processing libraries, it is always good to think about the core logic of what your library needs to do in terms of pipelines, where each step in that pipeline transforms the data in some way. And this is usually a very good architectural foundation to design your library around. So thank you very much. That's the QR code for the talk slides. And if you want to connect with me, you can scan that QR code. Thank you.
Thank you very much, Mohammed. Thank you very much. So now it's time for asking questions.
So I have two questions. I mean, one is PDF Core is quite a powerful library, but itself in real terms, it's an open source plugin to ANSYS because it needs ANSYS server running behind. So how can we, I mean, because it needs an ANSYS license to actually run it. And how good is it compared to ANSYS MapDL reader? Because PyDPF core also does the same thing what ANSYS MapDL reader can do. And my ANSYS MapDL reader is in true sense open source. It doesn't need a ANSYS license at the back end to run it.
Well, that's one of the reasons why I try to keep this presentation as generic as possible so that no one would ask me this license question. Well, I mean,
I have tried in my previous project, I was trying to fiddle with the finite element analysis images. And when I got the workbench files, ANSYS, I tried with PyDPF core, but couldn't process using that. And as a result, had to use MapDL reader.
Well,
MapDL reader was able to give me pretty good results. I mean, I was able to visualize all the nodes and meshes and the stresses.
So one thing I would tell you is that the maintainer of PyMapDL, if you know about MapDL reader, you probably know about PyMapDL as well. So is working on a feature that basically brings the functionalities that MapDL reader offers you into PyMapDL. And I think, I'm not 100% sure, that he is trying to leverage PyDPF for that. And if he is trying to leverage PyDPF for that, then at some point, maybe there would be like a special casing that, okay, for the functionality of MapDL reader, you shouldn't require a license since that already exists and it is completely open source. So yeah, that's the only comment I can give regarding that, unfortunately.
Because when I ran PyDPF core, it says that you need a server instance running, client instance running somewhere.
Yes, I agree.
That's thanks.
You're welcome.
One more question.
Thanks. It's a good talk. You spoke about how you would have a template for automatically generating all your boilerplate code. How are you ensuring that's properly tested? Are you having to manually generate tests for that, or are you also automatically generating those tests?
So in PyDPF core, the section of the code that is automatically generated, you can imagine that, okay, I showed you a chart of all this bunch of operators connected together to form a more complicated workflow. So you can think of that as the main computation engine of DPF. And these are very suited for this templating strategy. And because of that, we can as well more or less generate the test automatically. So every 24 hours, when we sync the Python client with the server side, as soon as all of these classes are generated, all of these tests are also generated simultaneously, and we test things before we merge. So the same way you use all this API shenanigans to get information from server-side objects to generate your classes automatically, you can also generate the test and essentially make sure that you don't have to do anything manually. Of course, the part of your code base that is going to be well suited for automatic generation is going to depend on the context. But once you identify those sections, you can as easily generate tests for those parts of your code base as you are generating the source files themselves. So I hope that answers your question.
Yeah, that's excellent. Thank you.
Okay, so thank you again, Mohammed. And now we're gonna have the lightning talk in the room 138. Thank you very much. And if you have any questions, you can ask your questions on Discord.
Thank you so much.
Yeah, I'm just entering the password and it's somehow invalid. 1 second. Okay. Uh, 1 second. I don't think so. Should work.
Is it asking for this additional screen on top or?
It's saying. Then what do I need to put it? Where? It's doing the screen and everything.
Is it going already?
Yeah. Oh, maybe. They disconnected the C1? I don't know. It's there, right?
Oh, that moves us down.
It is showing that.
Oh, they might have closed this.
They have?
I don't know.
Yeah.
Feels like they may have disconnected. I have like no idea why it is not working. That's so sad.
Maybe turn this on? I don't know. Although she didn't do anything, she directly took her bag and walked out.
Yeah, true. Also, it should not be something like that.
Is it this ring? Not sure. Even I don't know. Should I call one of the organizers?
Yeah.
Oh, what is it? Yay. Should I hold the mic? Sure. What should I do?
Just do the.
Okay.
Beginning. Just beginning. Do the beginning.
Okay. So hi everyone, I'm going to be presenting my topic unpacking parallelizing network X algorithms. So as a part of that, I am Akshata Sure. I am a BTech third year CS student. I am coming from India. I study in Indian Institute of Information Technology, Gwalior, and I have previous open source contributions in NX Parallel and Network X. And what I'm going to describe today is adding embarrassingly parallel graph algorithms in NX Parallel, which is a part of my GSOC Summer of Code project.
Yeah, you can check. If you still need more, I also take a small snap of the video. It's good?
Yeah, should I maybe come out once? Like, so that
Please come out.
just, yeah, I'll just hold one mic and look at that, and that's fine. So,